So on the sheet just before the link for this video, I want you to take a peek at that related rates exercise sheet that I have for you. Now, the very first question has an oil slick. Now, a certain amount of oil has been dumped in the ocean, specifically 2,000 cubic feet, but it's all been dumped in at once. And so it's in the shape of a circular disc, but it's not changing its volume as time goes by. But I do think as the height or the depth decreases, the rate is going to increase, and vice versa. And so my question to you, I don't have my glasses on, is this. The radius of the slit is increasing at a constant rate of 20 feet per minute. So the radius has a rate of change with respect to time t to be 20 feet per minute. How fast is the depth of the slit changing when the radius is specifically 25 feet? Now, basically what I'm asking is this. Can we find dH/dt when r is equal to, I think I said 25 feet. Now, it's too difficult for me to build an equation relating dH/dt to dr/dt. And since it's too difficult, what I do is I claim defeat. And instead, I just build a relationship between h and r. And it's typically so much easier to do that. And then once I have that relationship, I'll treat both r and h as functions of time t and differentiate implicitly with respect to time t. So here I go. Notice that this amount right here is a volume amount. So let's just, you and I go back to high school geometry and recall how to compute the volume of a right circular cylinder. Isn't the volume just the base times height? Now, that being the case, as time goes by, r is changing, h is changing, so I'm going to treat them as functions of time t. But as time goes by, v is not changing. So if you don't mind, I'm going to stick that constant in. But because r and h are changing, I'm not going to plug 25 in for r yet, not until after I differentiate. So like I said, treating r and h as functions in time t, I'll differentiate implicitly with respect to time t. But the derivative of this constant respect to who cares what variable on the left-hand side is this. On the right-hand side, there's a product rule application. But that can be this. Now remember, I'm trying to find dH/dt. So let's just plug everything in. Now that I've differentiated, I have a mathematical legal right to take out a mathematical camera out of my back pocket and take a snapshot in time. At this one point in time, here's what r is. And I admit r is changing constant that value, but in particular, at this point in time, that'll be dr/dt. Let me plug everything in. That's the unknown, that's what I'm trying to find. That dr/dt is given as 20. And if you carefully look at what I have on the board, notice I have a clear mistake. I didn't put the h in, but the h wasn't given. But I do think I have enough information to take a break and find the value for h at this one particular point in time. So pulling out a nifty piece of scratch paper. At this one particular point in time, let me use this original relationship. V is 2,000. It's equal to 2 times pi times r times h. At this one point in time, r is known. H is not. But look what I just did. I created a relationship, or shall I say an equation involving only one unknown. Piece of cake. So I do think now I see the value of h is simply this. Now solving for DHDT. Notice how technically speaking, this is a negative value, which actually makes a lot of sense because technically speaking, as time goes by, if R is increasing, H has got to be decreasing. Now, at this point in time, do you mind if you just very quickly stall and just double check all my arithmetic? Looks good. Okay, I can live with it.